Welcome, students. I am trying something a little different here today. I am not going to put my picture in the corner just to try to keep the file size a little bit smaller, the video size a little bit smaller. I am trying to work from home right now, and certainly, just as the case with many of you, my internet at home is not nearly as fast as the internet at school. So trying to deal with files is a challenge. Trying to keep it as simple as possible. But we keep learning and we keep moving along. So today is not Tuesday. I have the right spot on here. I'm in the wrong spot on my slides. I'm sorry. There we go. Today is Thursday, March 26, 2020. So, what are we after today? I can describe seafloor spreading and the ocean floor features that are produced by seafloor spreading. I can identify World War II technologies that led to the idea of seafloor spreading. So, here's our start. There is a problem with the continental drift hypothesis. So, the last video lesson that I had for you, we went over all this evidence for continental drift. The problem: how can a continent just go plowing around the Earth? Isn't there already crust occupying the space? So here's what I'm saying. If I have a continent, so here's my nice little Pictionary drawing. I have a continent over here, and here's the ocean, and of course there's something under the ocean. There's got to be some crust through here. So if this guy is wandering around, if continents are drifting, how does this move through this? It's already here. There's something already in this space. So that's a big problem. And so even with all the evidence for continental drift, the idea of continental drift didn't catch on. It wasn't accepted. Alfred Wegener was, from what I heard or have read, kind of ridiculed over the whole idea because he couldn't explain how it happened. So we're going to look at World War II. Seems like a little bit of a sidetrack, but there's a couple of technologies that were used in World War II, mostly or to a large extent, to try to find submarines. Submarines were a terrible weapon in the war, and of course, any navy needed to try to find those subs before they found you. So one of the technologies is echo sounding, or we commonly refer to it as sonar. So the technology, it had already been discovered. It had been actually attempted to use to find submarines back in World War One. But the technology was, let's say, developed and improved through the course of World War II. What it does is an active sonar ping. They emit a really powerful sound wave, and the wave travels outward, and then it bounces off of whatever objects it meets. And if we measure the time it takes for that ping to go out and for the echo to return to us, we can get the distance to the object. And if you're monitoring different directions, you get an idea of shape. So again, the wartime use was to try to find submarines. But a byproduct of that is when the war was done, and some of the people, you can watch videos on this. There's people that were involved in helping to develop and use sonar in World War II who had a scientific background. And when the war is done, they realize that, hey, we've got this information that, these sonar pings didn't just bounce off of submarines. They bounced off the ocean floor. And we have some features on the ocean floor And there were surprises. At the time of World War II, most scientists thought that the ocean floor was just basically a flat expanse of mud. So, to explain my little diagram, let's imagine here's a continent, and over here's a continent, and here's the ocean. And the floor is just flat, basically. Okay? You're going to have some sediments that fall in there. It's just a bunch of mud. Well, with the sonar data collected in World War II, it showed us that there was a lot more happening down in the ocean than anyone ever thought. There were rises, in some places even underwater mountains. And in other areas of the ocean, there were deep, deep trenches. So this, of course, when you find something that you weren't expecting and something that's new and different, a scientific mind is going to have more questions about it, and more questions means you do more research. You try to find out more. So basically, I realize that this is handwritten one. It's maybe a little bit hard to read. If you take a look in the background here, I have a map. And there's North America, United States. Here's South America. Here's Africa. Up here is Europe. Okay. And so by mapping the floor of the ocean, we see that basically kind of coming down the middle of the Atlantic, there's an underwater mountain chain. So the ocean isn't just, it doesn't just drop from North America down into the ocean, move across. Excuse me. There's features along the way, and so in this case, there's these high spots, and we call that now a mid-ocean ridge. This chain of underwater mountains, and the mid-ocean ridges run through many oceans in the world. Okay, there's also parts, and we call them deep sea trenches. So there's deep sea trenches often along the edges of continents, or sometimes along the edges of volcanic island chains. So here I have drawn in along the coast of South America, there's a place where the ocean gets really super deep. Another instrument used in World War II was a magnetometer. So a magnetometer is a device that measures the strength and direction of magnetic fields. And you guessed it, there were more surprises to be found in the ocean. So if you think, right here is a really crude drawing. So here's coming down from a continent, here's that ocean floor, and in the middle of the ocean we have this mid-ocean ridge. So it's raising up a little bit. So if you measure the direction of the magnetic field, so here's what's happening. When there are little crystals in some rocks that are magnetic in nature. And so if those crystals cool from lava, they line themselves up with the magnetic field of the Earth. And if we look at the middle of our Atlantic Ocean, I'm going to use the Atlantic for right now. If we look at the middle of the Atlantic, all those crystals seem to point to north in one direction. But if you go out to either side of that ridge, you'll find a stretch of the seafloor where the crystals all point the other direction. It's like north is south and south is north. And if you go further away from the ridge, they're back to pointing the normal direction. And if you go still further away, they're pointing to the other direction. There seems to be symmetrical stripes on either side of the ridge of alternating magnetic fields. Now, again, if you're a scientist and you see this, like, wow, this is something new. Why would this be? What's going on here? This is trying to give another picture. So that last one, I was trying to give you a profile of the ocean. So here is using North America, South America, Europe, and Africa again. And this is just an example diagram. But let's say right along that ridge, if you were measuring the magnetic field, you see that all points north, points this way. But on either side, there is a stretch of the seafloor where the crystals all point as if north was down here. And then you go further out, and it seems to be the regular direction again. And further out, it seems to be the opposite direction. There are stripes of alternating magnetic fields on either side of the ridge. So I'm not getting into the technology of this one, partly because I don't know it very well. But when scientists try to measure and estimate the age of this ocean crust, what they found out is that along the mid-ocean ridge was the youngest crust in the ocean. And if you go a little bit to either side, the crust is older. And a little bit to either side of that, older, older, older. And the oldest crust is the furthest from the ridge. In fact, in many cases, the oldest crust is kind of up along the edges of continents. So here's another picture of that, this time looking down on our map. So if you look down the middle Atlantic, right where that mid-Atlantic ridge is, the red line would represent the youngest crust that we find in the entire ocean. And alongside, on either side of the mid-Atlantic ridge, in this case the green stripes, that's a little bit older. And the blue stripes a little further away, they're older yet. And the oldest crust in the seafloor of the Atlantic is way out here near the continental edges. What's somewhat strange is, the oldest crust that we find in any of the oceans on Earth is only about 180 million years old. If we go on continents, we can go right here in central Wisconsin, and there are rocks that are billions of years old. So all of the oceans of the Earth are relatively young rock. Again, we got to add this up and see what does that all mean. So here's a conclusion. One, there seems to be some fundamental differences between ocean crust and continental crust. Why is the ocean crust always so young? Why do we get these weird magnetic stripes? Something different is happening in the oceans. So we get to the idea of seafloor spreading. What is proposed is that along these mid-ocean ridges, and here's my Pictionary diagram of the United States, here's Europe and Africa. Let's imagine that this is the center of the Atlantic, and along that mid-ocean ridge, new crust is being formed. What we have is volcanic action. Volcanoes are pushing up magma and lava out of the earth, and it's splitting apart and spreading apart there. So as it splits, the magma and lava fills in, and so it's forming new crust there. So as it moves away from that split, crust gets older and older and older. Seafloor is spreading. Now, think about this. If new crust is being made at mid-ocean ridges, but the Earth isn't getting any bigger. I'm deliberately pausing. I'm hoping that you're thinking about this. If new crust is being made, but the Earth isn't getting bigger, what else has to be happening? I hope that you are trying to think of an answer to that. But it seems like, well, there must be somewhere else where the crust is being destroyed. Because if we were just adding crust, there should be, swelling up like a balloon that's being inflated. But if we're making new crust and somewhere else the crust is being destroyed, then we can have, here's that word again, equilibrium. Remember that word? Now, the question is, where and how is crust being destroyed? So here's another great diagram where imagine this is my continent, here's my ocean. Let's imagine this is by the mid-ocean ridge. I didn't draw it raised up, but let's say right here we have the ocean is spreading apart. We have new crust being formed. And then remember those deep ocean trenches that we found some places? What if at those trenches, this was actually some of the crust being pushed down back into the earth? Well, now we've got a process where some places are making crust and some places are destroying crust. And so we can have an equilibrium on the earth. The earth stays the same size. Seafloor spreading gives us a partial answer to the continental drift problem. The continents don't have to plow through existing crust to move because that crust is being pushed back into the earth. It's being used up, destroyed, something. Now, of course, this leads to more questions. How does, what's the mechanism for how all this works? But that's going to be another lesson. So today we were looking at the seafloor spreading. See if I can find my slide again where we started. Here was our learning targets. I want you to be able to describe seafloor spreading and ocean floor features that are produced. So let's think about the features. We have mid-ocean ridges. That's one of the features. And we have deep sea trenches. That's another feature. The World War II technologies. We had both the use of sonar and the use of magnetometers. So that's today's lesson. Tomorrow, I hope to have some practice exercises for you. Today, you're also going to do a reading assignment. Again, always keep following along in Google Classroom. Please communicate with me if you have problems, if you are struggling. I myself, I'm struggling to try to keep up with things. I have a ton of grading to get through. I'm trying to check on, the different emails and messages from you, but we're all just going to try to do the best we can. And I need you. Some of you I've heard from every day in some context, and some of you I'm a little more concerned. Are you getting things done? Please spend your time every day working on things, and if you have problems, talk to me, call me. I gave you my cell phone number. Don't abuse it. But give me a call. Let's get things worked out. Hang in there. Stay safe. Hope to see you soon.